Now let's explore the calculus of parametric equations. So in the last section, we looked at what is a parametric equation, what's a parametric curve, and it is these two functions where we define x and y as two functions of another variable, the parameter, and that's what our parametric equations are. And then we get a parametric curve, and that's whatever the curve is that gets traced out as the parameter increases. Talked about direction of motion and restrictions on the parameter and all of those sort of things in the last section. But now we're going to get into, once we have a parametric curve defined by these parametric equations, what can we do with it with calculus? And what's pretty cool about this section is a lot of what we've done all the way through Calc 1 and Calc 2 so far, we can apply to parametric equations, and we can get corresponding equations for all the sorts of things that we did in Calculus 1 and Calculus 2, say for tangent lines, equations of tangent lines, finding the derivative, finding the arc length, finding areas, even surface areas. We can apply all of those same formulas to our parametric equations, and with some slight substitutions and that sort of thing, some explanations, we'll be able to use some adapted formulas. So let's get into it. So let's just quickly talk real quick about how do we deal with derivatives. And I have this box here, I'll explain it, but then we're going to head into an example and we'll go through it a little bit more. So if we had two parametric curves and f and g are both differentiable functions, and y is also a differentiable function of x, then it would follow that the derivative of y with respect to t, using chain rule, would be dy dx times dx dt. And as long as dx dt doesn't equal 0, we can actually solve for the derivative of y with respect to x in terms of the derivatives of the two parametric curves. And we end up with this pretty simple formula that the derivative of y with respect to x is just going to be the derivative of y with respect to t over the derivative of x with respect to t. While I have this box up, I'm just going to talk real quickly about the second derivative. We can even apply the second derivative to this, and just applying the second derivative, what we find is that the second derivative of y with respect to x, both times, we end up taking the derivative of the derivative we have above, and so we get the derivative of the derivative divided by dx dt. And that ends up being our second derivative. So those are the two formulas that we're going to use. I just wanted to go over them pretty quickly right here. But I want to spend the time in the video more on the examples. So let's take a look at this first example. So this first example, and I won't go through the time to talk about graphing this curve. I use Desmos. I just grab the image, set it up ahead of time. And if the curve itself is defined as x equals 2t squared plus 1 and y equals 1/3 t cubed minus t, if the first thing we want to do is find the equation of the tangent line to the curve at t equals 3. So when the parameter equals 3, what would be the equation of the tangent line? So let's do that. So for the equation of the tangent line, we need an actual line. We need y equals m sub tangent, whatever the slope is of the tangent line, times x plus b. So that's what we're looking for, equation of the tangent line. So if we want an equation of the tangent line, we're going to need a derivative because we need the slope of the tangent. So the slope of the tangent is going to be equal to dy dx. But we just talked about in the very first part here, we talked about how that is the same as taking dy dt and dividing by dx dt. That's how we define the parametric derivative. Dy dx is going to be dy dt over dx dt. So if that's the case, then I need to actually find those two derivatives. What's the derivative of y with respect to t? What's the derivative of x with respect to t? So let's go ahead and start there. My parametric equations are up there, but I'm going to carry them down here so we can use them in the example. So x equals 2 t squared plus 1 and y equals 1/3 t cubed minus t. And let's go ahead and take the derivatives. We're going to come back and look at where this actual tangent line is on that curve. But for now, let's get in here and take these derivatives. So the derivative of x with respect to the parameter t would just be 4t. And dy dt would be t squared minus 1. And so our derivative, dy dx, is the ratio of those two. It's going to be t squared minus 1 over 4t. Okay, so now we need the equation of the tangent line. It was at, let's just verify that real quick, make sure I got the right t, at t equals 3. So if we want it at t equals 3, at this point we could actually find the slope of the tangent line. So now we could actually find what the slope of the tangent line is, because I know the point at which I'm looking for the tangent. Actually, I don't know the point, I know the parameter. I know t equals 3, so I could plug that in and I could find the slope of the tangent line is going to be the derivative, dy dx, evaluated when t equals 3. And so I could actually plug that in. Let's go ahead and get that. So that's going to be 9 minus 1 over 12, or 8/12, or 2/3. Okay, so we know what the slope of the tangent line is, but we're asked not just to find the slope, but the full equation of the tangent line. So I got to come up with my y-intercept as well. So I know that the slope is 2/3, and the other thing I need to know, which was not actually given in the problem, we have to do just a little bit of work, I know that the parameter equals 3, but what point is that actually on the curve? So what point would that be on the curve that I have graphed here? Where would that ordered pair be in the xy plane? So we do need to find that. So we need to find, because that wasn't given. Sometimes it's given, but what I also need to do is we need to find the point on the curve when the parameter equals 3. So we need to find that point. So that's simple enough to do, though, because I have the parametric definition. So I just plug those in. So x equals 2 times 3 squared minus 1. Let's see, what would x be? That would be 9 times 2, 18. I'm sorry, I put a minus right here. Plus 1. 18 plus 1, that would be 19. And y would be 1/3. 3 cubed minus 3. So that's what? 27, 1/3 of 27, 9 minus 3. So that's going to be 6. So we know that the actual ordered pair is 19/6. So when t equals 3, it's actually passing through the ordered pair 19/6 on the curve in the xy plane. So 19/6, I mean, if we were to zoom in right here, 19, you know, 20 is actually, just realized that that 20 is actually one over there. So this is right here. Get my ruler. I could even bring my ruler in here and draw the exact tangent line here. Okay, so that is the equation that we're actually looking for right there. That is the point. That ordered pair right there was the ordered pair 19/6, and we are looking for the equation of that tangent line. We already know its slope is 2/3. We figured that out, but we still need to put that into an equation form. And since we now have the ordered pair 19/6, we can put it all together and we can say, okay, so now let's find the equation. So the equation of the tangent line, just using a little bit of algebra here. I'm going to use the point slope formula. So I'm going to say, and you don't need to do this, you could find your b in a different way. Lots of ways to work with lines here, but I'm just going to go with this. All right, so we've got y minus 6 equals 2/3 x, y minus 6 equals 2/3 x minus 38/3, and then we'll add the 6, and we'll get 2/3 x. Let's see. So that would actually be 18/3, so we end up with minus 20/3. And that is the equation of the tangent line at t equals 3, which happens to pass through that ordered pair 19/6. So let's check this out. And there it is. So there it is. Try to get it all on the screen here. Kind of got small, but there you can see the equation of the tangent line. You can see the parametric curve, and you can even see the tangent line. We drew the tangent line there at 19/6. Okay. So kind of a little review of tangent lines applied to our curves that we've now been discussing, which are those parametric curves. All right. So let's do the part B. So if we want to know where the horizontal and vertical tangent lines are to the curve, and let's do it for the same parametric curve that we're looking at. Let's find the horizontal and the vertical tangent lines to the curve. So remember that horizontal tangent lines are going to occur when dy dx equals 0, and those vertical tangent lines are going to occur when dy dx is undefined. So if we can zoom in here and look at kind of this little review / application, it starts with a review, right? What is a horizontal and vertical tangent line? A horizontal tangent line is when the derivative with respect to x, dy dx, is equal to 0, and a vertical tangent line is when dy dx is undefined. But we're going to expand that now into our new definition for a parametric derivative. Dy dx is dy dt over dx dt, as long as dx dt doesn't equal 0. And so when we apply that, we're going to have a horizontal tangent line when dy dt equals 0, when the numerator equals 0 here. We do have this little caveat. We have to make sure that we're not getting a 0 over 0, so that would be provided that dx dt does not equal 0. If they actually both equal 0, if your dy dt and your dx dt both equal 0, so let's make a little note here. Note, at a point where dy dt equals 0 and dx dt equals 0. dy dx would actually be equal to a 0 over 0, which is an indeterminate form. And you would want to look at a limit as t approaches whatever that parameter value is. Let's just call it a, as t approaches a of dy dx, ... So we'll try to do an example, maybe like one of those, either in another video or in one of the class sessions, because sometimes that happens that both dy dt and dx dt are 0, and that would make your dy dx a 0 over 0, and then you just have to consider what that means, right? We're really bringing, what's nice about the end of Calc 2 is we're bringing just so many little pieces that we've talked about before. We're bringing them together and applying all these tools that we've built up over time to either new functions or new ways to express functions and so forth. Okay, so we will have vertical tangent lines. Sorry about that little tangent. It's a little math joke. I went on a tangent while talking about tangent lines. Okay, so the curve has vertical tangent lines when the denominator, dx dt equals 0, which means we have that undefined. Again, provided that the numerator is not also equal to 0. Okay, so let's get into it. So let's take a look at this example that we were working with. So for this particular curve, if I could get it back up here, I think I'll do part B over here. So for this particular curve, x equals 2t squared plus 1 and y equals 1/3 t cubed. Let's now find the horizontal and the vertical tangent lines to this curve. So let's look at horizontal and vertical tangent lines. So we already have the derivative, and so I'm going to go ahead and just bring that over here. So the derivative was, here we go. We already calculated the derivative for this particular curve because we did that in part A. So let's just simply bring that over here. We already have the derivative. The derivative from part A is t squared minus 1 over 4t. And so now let's consider where would we have horizontal tangent lines. Well, horizontal tangent lines are going to occur. And again, this portion is review from Calc 1. Horizontal tangent lines occur when the derivative, the rate of change of y with respect to x, is actually equal to 0. So when the derivative equals 0, so I mean there's, we talked about the formulas over in the box a second ago, but the formula should be pretty intuitive and really just an extension of what you already know, because dy dx is going to be equal to 0 when this numerator, by the way, this numerator came from dy dt and the denominator is dx dt. So that happens when dy dt, the numerator here, is equal to 0. So when t squared minus 1 equals 0 is when we're going to have horizontal tangent lines. We solve for t, we would find that t is equal to plus or minus 1. Now, note that that is when the parameter, that's the values of the parameter. When I look at that, though, that does not actually give me the points on the curve where we have those horizontal and vertical tangent lines. And I should have added, let's go ahead and draw those in as well. So we don't know yet where on this curve, I can see where those are going to be. They're going to be about like, whoops, there and there. But I want to get in there and I want to actually know exactly what that ordered pair is where those two horizontal tangent lines occur. So I know what the value of the parameter is, but I still have to go back and figure out what the ordered pairs are where they occur on the actual curve. So now let's find the ordered pairs, find the points on the curve. And all we have to do here is plug in our parameter into our parametric equations. So t equals -1 and t equals 1, and I don't have my parametric equations right in front of me here, so I'm going to just copy them so we've got those over on that other screen. So let's just copy those two parametric equations, so they'll be at the top of the screen here. Okay, so when t equals -1, we would be at the ordered pair, plug -1 in for x there, and that is going to occur at 3, and plug in -1 into y, and let's see, we'd have a -1/3 plus 1, so that is going to be at 2/3. Okay. And then same thing, plug in 1. When I plug 1 in for x, I'm going to get 3. When I plug 1 in for y, I'm going to get 1/3 minus 1. So I actually get minus 2/3. So those are the two places on my curve where I have horizontal tangent lines. So I can go back to the curve and I can say at 3 and 2/3, let's zoom way in there and get the ruler out. And at 3 and 2/3, so right there, we have a horizontal tangent line. And right it's a little bit lower there. We have our other horizontal tangent line. So this, by the way, this one was occurring, so these are the two ordered pairs. This was 3, let's make that a little bit bigger. This was the ordered pair 3 and -2/3, and this was the ordered pair 3 and +2/3. This parameter, the 3 -2/3, was occurring at t equals 1. And this was occurring at t equals, not 0, -1. There we go. Okay. By the way, this one up here where we did this tangent line from part A, this was at t equals 3. And so we're starting to get a good sense, actually. We have the direction of motion at this point. We'll trace that on in a second after I get the vertical tangent line on here too. But we've got the direction of motion. We can see the way this curve is traced out. So through doing these derivatives, we're actually getting a bunch of information about the curve itself too. Okay, so one last piece, let's figure out where that vertical tangent line is. And so we're going to have our vertical tangent line. Our vertical tangent line, or tangent lines, are going to occur when the derivative dy dx, again, a little bit of review, vertical tangent lines occur when your derivative is undefined, and our derivative is going to be undefined in this parametric scenario when the denominator, which is dx dt, is equal to 0. So when does that occur? Well, when does 4t equal 0? It's going to equal 0 when t itself is 0. So when t equals 0, what is the points on the curve? So the same thing, find the points on the curve. There's actually only one here. Find the point on the curve where that happens. And when t equals 0, when we plug that into my parametric equations, we are going to have the ordered pair 1, 0. And so we have a vertical tangent line at 1, 0. So our vertical tangent line is occurring at 1, 0. We could see that on the curve up here. We didn't know what the parameter was at that point. But right there, if I zoom in and I put my ruler there, there's my vertical tangent line. Let's scoot it over just a little bit. There is the vertical tangent line, and that point right there was at 1, 0, and that was when the parameter equals 0. And just as a note, one of the things I mentioned when I was up here on the curve a second ago when we were talking about graphing those tangent lines, horizontal and vertical tangent lines, as you start to graph these things, the horizontal and the vertical tangent lines, we start to get information about what's happening on this parametric curve that we could use. So for instance, if we were asked to state the direction of motion, well, after we've done this, we know the direction of motion because we can see that as the parameter increases, we're going this direction. T is -1, and then 0, and then 1, and then 3 up here, and so it must be the direction of motion was gained. That knowledge about the direction of motion was gained as we graphed these points. And so we're getting all sorts of things as we do this. And the other thing is we can take second derivatives. I mentioned the second derivative, but I wanted to just also say that second derivatives can be used to find concavity of the curve. So if we wanted to take the second derivative of this, we could take the second derivative by taking the derivative with respect to t of the first derivative over dx dt. That's the formula for the second derivative. And we would see where we've got concavity. We could look at where it's concave up, concave down, and we could figure out what values of between which values of the parameter we have those scenarios. So we can do a lot of the same things that we did with explicit definitions for functions. We can do those with our parametric curves as well. Okay, that's our first example, our example of working with derivatives, first derivative, and looking at vertical, horizontal, tangent lines. And we'll come back and we'll do some areas and arc lengths and surface areas in some more videos.